not 1 2 3 4ครับ Hello student I'm going to show you about the extra example that I posted into the Facebook and we consider the first problem that's going to talking about the frame. This frame has the point A as the pin, point C as the pin, and also the B is the hinge of the pin. And if you consider this frame is subjected to the triangular load of 4 kilonewton per meter, the question they start by asking us to determine the reaction. If you consider the whole frame, you can see that by checking the member, you can see the member BC is the two forces member. Why? Why is the two force member? Because the point B and point C is the pin or the hinge, and between the point B and point C there is no forces. So that means the member BC is going to be the two force member. That means it's going to be in tension or it's going to be in compression. And also, if you consider how the structure reacts under the force, you can see that under the force, the beam AEDE is going to rotate, something like this. That means what? That means the member BC gonna react to balance it. That means the force as the point B acting on the beam is going to be in this direction, is upward direction. That means the member BC gonna be in what's so-called in compression. If we consider this, we can start to draw the free body diagram of the beam. So we start by the free body diagram of the beam AEDB and the column of the BC. And then we will use the equation of equilibrium to determine the reaction that occur on the structure equilibrium. Okay, and by doing this, let's check how long is this one. Let's make it by do some kind of copy. Let's check this one is about 5 centimeter. So this one is going to be the beam. This point is A, this point is B, and make it half at point D, in which the load going to apply over here for 4 kilonewton per meter. So this is going to be the triangular load and apply is over here on the right hand side and over here on the left hand side. This is 4 kilonewton per meter. So also we supposed to set the XY reference axis. Let's say this one is the Y, this one is the X. And the beam ADB under the application of this force, as we mentioned, the force on the member BC gonna to resist in this direction to balance the rotation due to the triangular load clockwise. This one supposed to be in the counterclockwise direction. So by setting things like this, our member BC is subjected to the compressive force, and then this is B, this is C. Let's set the force here as the F sub, and following this one, F sub BC, and then the A. The A is the pin. So the force as the A is supposed to be at the A sub Y, and in this direction is going to be A sub X. And then else, the distance, this is going to be 3 meter, this is going to be 3 meter. So according to this, we will have the length like this. And also what? The direction of the member BC. This is 3 meter, this is 5 meter. So according to the ratio of here, as we know, this is going to be 3, this is 5. So everybody know that this is going to be 4. Okay, this is the free body diagram of the structure. And also, if you go further, the force F sub BC here is going to be what? Will you separate it? This is in vertical. This is 3. It's going to be 3 over what? Over 5. And then it's going to be F sub BC. And in another direction is here. Here is in horizontal direction. It's going to be F sub BC. And then this is 4. It's going to be 4 over 5 F sub BC. Okay, that is going to be very complete free body diagram of this. They ask us to determine the reaction at the support A and the joist B. That means for the A sub X, A sub Y, and F sub BC. By doing this, we have 3 equations of equilibrium. Summation of F sub X equal to 0. Summation of F sub Y to 0. Summation of F sub moment equal to 0. We start by taking the moment at point A to eliminate the unknown A sub X and A sub Y from our equation. So we can determine F sub BC easily. F sub BC, you can see this one produce no moment. It's point to the point A. This one going to produce the counterclockwise direction. So the first one is 3.5 F sub BC. And this one is 6 meter from point A. So we can see this one times 6 meter. And the force that's X over here is supposed to be has the resultant force here due to the symmetry of the triangle. This is going to have the resultant force of 1/2 of 6 and times 4. If you push this one into the calculator, this one gonna be 3 and this one going to be exactly 12 kilonewton. So this one gonna be 12 kilonewton, and this one 12 kilonewton is going to be 3 meter from point A. So it's going to be times 3 meter. So this one cut, this one cut, this one to be 2. And then our F sub BC is equal to 12 and then times 5 for up and then divided by 6. And then this one cut, you're going to get this one for 10 kilonewton. So the first one, we obtain F sub BC is 10 kilonewton. Put the answer over here. And then we still have we need to find what? Summation of F sub X equal to 0. Okay, the summation of X sub X equal to 0. A sub X is in this direction. So A sub X is equal to what? This one equal to what? This one equal to this one. Equal to 4 over 5. And then F sub BC is 10. So A sub X is 8 kilonewton. Okay, that is for the A sub X. Just put this one 8.0 kilonewton. Okay, and then what? And then we can find summation of what? Summation of F sub Y equal to 0. So this one is upward positive. Our A sub Y is upward. This guy is plus. This one is 0.6. This one is 10. This one is going to be 6 kilonewton. And then this is up. This is up equal to 12 kilonewton. So if you compute this one, you can get A sub Y easily equal to 12 minus 6. That means 6 kilonewton for the A sub Y. So put this one is 6.0 kilonewton. So we finish this calculation and then we get the reaction at point A and also the reaction at the joist B. So that means this one, we get this one for 10 kilonewton, and this one also 10 kilonewton. So the resultant acting at the point C is 10 kilonewton. If we like to find the reaction C sub X, C sub Y, I think I ask you guys to determine what is going to be the reaction C sub Y, what is going to be the reaction of C sub X kilonewton. Give it at your assignment, okay? And then later, they ask us to determine the normal force and also the what's so called the shear force, and also determine the bending moment at point E. So where is the point E? You get to go back, and this is going to be the point E, and the point E is at what? At the middle of the portion AD. So that means this is going to be the point E, 1.5 meter, and they are asked us to determine the internal forces and internal moment. We can do it by the same thing. We cut this one, we cut this portion of the beam, and we are going to draw the free body diagram. And second, draw the free body diagram of what? Of A, E, and what? And use equation of equilibrium to determine the N, the V, and the M. Okay, by cutting this, we got the portion of the beam like this, and then this one is A, this one the E. What we have is what? This is in the reference of XY axis. We know the force here, A sub Y. The A sub Y, we have previously of what? A sub Y of 6 kilonewton. So this one is going to be 6 kilonewton. And we also have A sub X. A sub X is 8 kilonewton here. So this is 8 kilonewton. Under the application of this, we have the force, and then is the triangular force. And due to this, the value of force here going to be determined by using the triangular angle. By consider the slope, this is 4 divided by 3. So the slope, consider the slope, and this one going to be 4, and then divided by 3. The slope there is going equal to what? Equal to this one is W divided by half of this is 1.5 meter. So this is 1.5. So if you push it into the calculator, W is going to be what? 2 kilonewton per meter. So this is 2 kilonewton per meter. Okay, and this one cannot be in equilibrium without the what? Without the moment here. That is going to be M sub E. And if you go further, you're going to get this one for the V sub E. And the last one that we're going to have, this one is going to be N sub E. And following this is going to be very easy. Summation of X sub X equal to 0. This one is positive. So N sub E is going to be 8 kilonewton. Okay, that is the first one for 8 kilonewton. You can put this one for 8.0 kilonewton. And then if you do the summation of F sub Y equal to 0, this is going to be downward. Our V sub E is downward. The force here also need to have the resultant. The resultant of this is going to be 1/2 of 1.5, and then this one is 2. So if you push it, it's going to be what? 1.5 kilonewton. So this is plus 1.5, and then it's going to be equal to what? This is V sub E. This is equal to 6 kilonewton. So this is 6 kilonewton. So by doing V sub E going to be 6 minus 1.5 and it's going to be 4.5 kilonewton at this section. So answer this. You're going to get this one for 4.5 kilonewton. Okay. And then the last one that we're going to have is the moment. You do the summation of the moment at point E, okay, and then equal to 0. Your moment is what? Your moment is counterclockwise, is positive. Your M sub E in this direction. If you take this one also in the same direction, plus 1.5. However, the distance here is what? Is only 1/3 of 1.5. So it's going to be 1.5 divided by 3, which is going to be 0.5 meter. And this is going to balance by this one. This way is clockwise, counterclockwise. So it's 6 kilonewton and the distance is 1.5 meter. You put them into your calculator. Your M sub E can be determined easily as 8.25 kilonewton meter, and it is positive moment. Positive moment gonna produce this kind of deformation. The top is going to be in compression. The bottom gonna be in tension. Okay, that's going to help you. The shear is downward. Okay, this is positive, is downward. That means the shear stress gonna be in this downward direction. So answer this one. You got this one as 0.25 kilonewton meter. Okay, now you move to the mechanics of material. The knowledge that we work on this portion of this problem is the engineering static. So we come to what we have. This time they ask us to determine two things. One is the transverse normal stress distribution. This is the distribution of transverse normal stress. Another one is the what's so called, I think this one's supposed to be normal stress. This should be to be normal stress distribution. Is the distribution of the normal stress or the distribution of sigma. This is the distribution of tau. Okay, this one is not kind of correct. Okay, this is going to be the normal stress. And from the equation that you have on the top, this is normal stress due to what? Due to the N sub E. This is the normal stress due to the moment M sub E. So the normal stress will come from two portions. However, the shear stress comes from this. This is for the chapter 7. This is for the chapter 6. You got to go back and review it. This is for the chapter 1. Okay? By doing this, what we have, let's go by finding the normal stress first. Okay? And by doing this, that is going to compose two things. One is going to be equal to. One is going to be the normal stress due to the bending, and this one is going to be the bending. Another one is going to be plus. Another one that's going to be from the normal stress. So this one is going to be sigma equal to my over I, and this one is going to be sigma equal to n. This one n sub e divided by a. This is m sub e. Okay, and you know that due to the bending, something like this, this is in the compression, this one is in the tension. Okay, and then there is some points that's in between of this. This is 2.5 centimeters. So this is going to be a half of this. This point going to be the point of zero stress. And then this one, let's say this one is going to be, if you put this one very big one, this is going to be compression. And this one going to be the stress, something like this. This one is in compression. This is compression. Okay. This is going to be in tension. And Also, due to the double symmetry of the section, this one going to be equal and in tension. We have this one and this one. Okay, this is occur passing through the point of the centroid of the section, and then we call this one as the neutral axis. Okay, axis, neutral axis, or NEU. Neutral is the middle, and then axis. And then what we have is this is in tension. This is in tension. The N is what? Is compression. Okay, the N is compression, which means it's going to produce compressive stress. And then due to from the knowledge from chapter 1, due to this N, the stress occur on the section could be averages and computed by this equation. Okay, let's see. What is this going to be? Okay, this is sigma going to be. This is the normal, the moment here is 8,250, and then this is Newton meter. Okay, and then the y is the distance you measure from the neutral axis to the top and to the bottom. This guy has the same one. Okay, same one of what? We have the section. If you recall from what we have on the top, just put it over here to be the reference. This is going to be 50 millimeter, and the depth going to be 100 millimeter. Half of this going to be 50 and 50. So this is the section that we are interested in without going back to the top. Okay, this is going to be 50 millimeter. This is 50 millimeter, and this is again is the neutral axis. This is the centroid of the section. That's mean of what? That's mean this one going to be 50 millimeter. This one also 50 millimeter. So what we have now is just put this one into the equation 0.050 meter, and then we have what? The I. The I is going to be I sub NA is going to be 50. Okay, that is going to be 0.05, and then 0.1. This is 100 millimeter cube, and then divided by 12. If you put this into calculator, this one going 4.167 and 10 minus 6 meter power 4. So you put this one 4.167 10 minus 6 meter power 4. So this one cut power 4 change to power 2. That is going to be Newton per meter power 2. If you put this thing together, you may get this one as what? Okay, 99.0 10 power 6 Newton per square meter, or it's going to be 99.0 megapascal. So that is going to be 99 megapascal. This one also 99 megapascal. And then we come to the axial stress. That's due to the N sub E. Okay, N sub E is what? N sub E is 8,000 Newton. That is 8,000 Newton. If you divide the section by millimeter, that is going to be 50 and then 100 millimeter square. And you know Newton per square millimeter, you got this one in the megapascal. So put them together, you get this one is 1.60 megapascal. Okay, and this is what? This is compression. This is what? This is also in compression. So it's going to be add up. So this one is in tension. However, this one is in compression. This one will be reduced. By combine them together on the chapter 8, we can combine this thing together based on the assumption of linear elastic. Okay, we can combine stress together, and very small deformation. There is more deformation. That's going to be follow our study. And then the stress over here going to be add up. This is going to be 1.6 megapascal plus 99. This is going to be 99.1.6. That is going to be 100.6 megapascal. So this is going to be large compression. Okay. And then what? On the bottom, this is tension, this is compression, is going to be reduced by 99 minus 1.6. Okay, 99 minus 1.6. That is going to be 97.4. This is going to be in tension, but smaller than this. That is 99 minus 1.6. That is 97.4 megapascal. And at the middle, now, what we have is what? This is going to be 0. This is going to be 1.6. So this is going to be stress in compression. By doing this, you can draw the triangle again. But this time, what we have is the neutral axis shift from the red line to the dash blue line, and this one is going to be the tension. So now our stress distribution by the combine of normal stress due to the moment and normal stress due to the axial force, we get the new one of the normal stress distribution as required. But the problem is the neutral axis right now change, and usually we just set following this. We just set this one. Let's set this one as the distance of y, and the total length of this is 100. That means the position here will be 100 minus y. We can determine the location. We can determine the location of new neutral axis by using the similarity angle. Okay, by similarity angle, you can see this is going to be 100 minus y, and this is going to be the distance of y. So 100.6 is going to be here divided by 100 minus y, and this is going to be equal to the slope here 97.4, and then divided by over here distance of y. If you push everything in your calculator, the new location of the y is going to be 49.2 millimeter. This is the position of this. This is going to be 49.2 millimeter if you measure from the bottom. Okay, you can get this, and this is going to be the normal stress distribution. We still have one more. This one is the shear stress. Due to the symmetry of this, the equation that we use to compute the normal stress is based on tau equal to VQ over IT. Okay, the V on the section, the V on the section always the same. It's going to be V sub E. The I on section also the same. The I is the same. And the T, now the problem, the T is the width of the section. The T also the same. So what is going to control this equation is the Q. Okay, Q is the area. Above what we find the tau. If we like to find the tau here, the area above here is 0. So the moment, the Q is the moment of the area above neutral axis is 0. So usually we know that on the top and the bottom and always like this of the section, we'll have the tau equal to 0. And then if you go back to the PowerPoint of chapter 7, the Q is what's so-called the area, okay? And then time the D, and you can see the Q is in the dimension of length power 3. And since this one change with the Q, so the curve of this is always what? Always have the curve like parabolic equation. As you know, due to the parabolic equation, the curve will have the shape like this. Okay, due to the symmetry, the top and the portion gonna have the same what? Same shape. And the tau max for this is going to occur when the area is maximum. The area is maximum is occur as the previous neutral axis. So this is the point of tau max. Okay. And if you further to the chapter 7, tau max can be easily for the design. Tau max can be determined from 1.5 V sub E divided by E. And if you do this, it's going to be 1.5 V sub E is what? 4,500 Newton. And then divided by the area. The area is 50 times 100 millimeters square. 50 times 100. This is millimeters square. This is Newton. The unit of Newton per square millimeter is going to be in megapascal. Okay, we can see and put the number into the calculator. This is going to be 1.5. Okay, อาจารย์ if I use this equation to find this, how can I do it? Okay, don't worry. This tau at what tau max will from what? We from this one V sub E, and then it will be come from Q max divided by I, and then another one is the T. Okay, the point we are looking for produce the maximum Q again is here. That means what? Again we put this one 4,500 Newton. 4,500 Newton. That is going to be V sub E, and divided by I. I is 4.167 10 minus 6, and then meter power 4. The width is this one. That is going to be 50 millimeter. So put this one for 0.0 meter. Now the problem is to determine the Q. Again, the Q is the area. The Q is the area. Let's put this area here. Okay, and then the area is going to take the moment from the centroid of this area to the neutral axis of the section. So this is going to be 50 millimeter. This is going to be 50 millimeter. That is 0.05 times 0.05. And then what? The distance here is going to be half of the 50 millimeter. From here to here, that is going to be 0.025. And then you put them together and do some calculation. You will get tau max in this one as what? 1.35 megapascal again. Okay, and then they ask us further to draw the stress element. Okay, find the stress as point E. Okay, find the stress at point E. Point E is what? Point E is in this direction. Point E is about this. Okay, this is what? 20 millimeter. So the top portion of this is going to be 30 millimeter. Okay, sorry. Okay, if that case, we just find what the point is supposed to be about here. Okay, you measure what 20 millimeter from the bottom here, from the bottom here. So we have to determine this. This is going to be tau sub e, and this is gonna be sigma sub e. Okay, and the tau sub e, as we discussed before, the v sub e is downward. When e sub v is downward, so the tau here is going to be have the downward direction also. That means the shear here going to be in this direction. That is tau sub e. And as you may know, for the tau, if this one down, this one must be up to balance the force in the vertical direction. And if you take the moment here, see, the red has produced no moment. The blue gonna produce clockwise. So we need this one to balance it. And then here they come, you got to have the horizontal balance by this one. This is going to be tau sub e. Okay, that is going to be in downward direction. And also, this one sigma sub e is in tension. That's for sure. Over here, that is going to be the stress. That is going to be sigma sub e in tension. And this sigma sub e also called sigma sub x. And also tau sub e is called tau sub xy because we consider this is the x and this is the y and this is point E. So what is the value of this? Okay, by doing this, you can compute sigma sub e in two ways. One, go back and use this equation. Okay, or another one, you use the similarity angle. Okay, by using similarity angle, this is sigma sub e. You may have this is sigma sub e, and the distance you have here is what? This is 49.2, and this is going to be 20. So that is going to be the distance here and here, 49.2 minus 20. And that's one going to equal to this one, 97.4 divided by the whole length here of y, 49.2. Okay, by doing this, you push them into your calculator. Your sigma sub y gonna be 57.81 megapascal. Okay, that's very easy to find, right? Okay, next, the tau sub e, tau sub e, you must compute basis on this same thing. Okay, it's going to be v sub e, 4,500 Newton, and then the same thing divided by the same RIT, 4.167 10 minus 6 meter power 4 and 0.05 meter. The change is going to be the area. Now, at this point, the area you are considered is going to be here. The area going to be here. The area is what? This is 20 millimeter. This is 50 millimeter. So 0.02 times 0.05. And then what we are looking for is the distance from the centroid of the section measure to the neutral axis. Okay? By doing this, this is a total of 50 millimeter. This is 20. Half of this here is going to be 10, right? So this is going to be 50, the total. Minus this one, minus 10. This is going to be 40. So this is going to be 4040. And then all of this is going to be in meter. If you push everything in your calculator, This is 0.864 megapascal. Okay, this is going to be your answer. This is going to be 0.864 megapascal. Okay. And then I would like to make the assignment for you guys. If you prefer, if you tie, please go back and tie the other point. This is the point E. Let's say if you put this one another 20 millimeter, and then can you find the stress element here? Okay, or if you measure this one for 25 millimeter at this point, can you determine the stress element for that point? The stress element is always the question that we looking for, because after this we will use the knowledge of stress transformation to determine the principal stress to determine the maximum shear stress. Okay, let me finish this problem here, and we will use this stress element in the chapter 9 stress transformation. Okay, have a good day.